In today's video, we're going to look at logarithmic functions, exponential functions, and their inverse relationship. We're also going to look at transformations of logarithmic and exponential graphs. Well, we need to make sure you have the background for this, so let's start with a quick logarithm review. If I'm looking for the base 3 logarithm of 81, I'm trying to solve this problem right here. 3 raised to what power makes 81? It takes 4 factors of 3. 3 times 3 times 3 times 3 is 9 times 9, and that's 81. So the missing exponent is 4. And that's what a logarithm is. That's just one example. But in general, a base b logarithm of a number x is equal to y if and only if that y is the exponent that sits on that base to make what's inside of the logarithm, the argument of the logarithm. Okay. Now, we also want to know what functions are. Which of the following are functions? Now, what is a function? It's a set or a collection of ordered pairs, either finite or infinite, where a certain rule is followed. Each of the first elements in these pairs is paired with only one second element. Each x is assigned a unique y. Now, it turns out most of these are functions, and this first one certainly is. So, for example, if I go to x equals 10, and I ask, well, what's the y that's assigned to 10? You can answer that question without ambiguity. When x is 10, the assigned y value is 4, and there is no other assignment to 10. So this one is a function, pretty clearly. And it's not just the 10. You have to check through the entire list. Contrast that with this collection called R. It is not a function. So when you write down something like, R of 8, you're asking the question, when x is 8, what y goes with that x? What's the y assigned to 8? Well, here it seems to say -1. Whereas up here, it seems to say that 4 is assigned to 8, and that's ambiguous. So we can't have 2 or 3 y values assigned to the same x if we're going to have a function. So this one is no. Some people get distracted by s. They'll see all these 2's over here, and they'll think, well, that can't possibly be a function, but it is. Just think of the definition. Each x is supposed to be assigned exactly one y. So pick an x, like 7, and say what gets assigned to 7. Well, it's a 2. There's no other place in the table where 7 appears assigned with some other number. And that brings us to example P in this table. X's and y's are assigned. I'll get students who will see this 8 appearing twice and immediately jump to the conclusion that they're not looking at a function when in fact they are. When x is 8, the assigned y value is 4. And you didn't get some different assignment up here. So this is a function where somebody just wrote down a duplicate pair, but that doesn't disqualify it from being a function. One other term you might not be familiar with is one-to-one functions. In a one-to-one function, you not only establish that you have a function in the first place, but the rule about, each x gets assigned just one y, it actually works backwards. Yes, so for example, here's y equals 6. What x gets assigned to 6? Well, it's just 2. There's no other place in the table where there's a y equals 6 being assigned some different x. This is a one-to-one function. Hopefully it's a lot like if you think about all the people in the world who own just one toothbrush and use just one toothbrush. So each person has just one toothbrush. That's a function. But each toothbrush hopefully is used by just one person. And that's a one-to-one function. This is not a one-to-one function. Because when y equals 2, there's all kinds of different x's getting assigned. And I bring this up because it turns out today's big topic is inverse functions, And in order to have an inverse function, you have to have a one-to-one function. Let's take a look at a couple of inverse functions. Inverse functions are functions that have this property that whatever the first function does to a number, the second function is capable of undoing it. So for example, square root of x operating on a 25 takes it down to the power, or takes it down to 5. Well, this x squared function, I'm calling it g, has the property that it can take the 5 and restore it back to 25, which is the number we started with in the first place. So this is often written something like this. If f and g are inverses, then f of g of x has to seem to have no effect on the x whatsoever. Start with an x, end with an x. But also g of f of x has to give back x. So let's do the example I just talked about. And we'll do it from here. And we'll start with 25. So x equals 25. All right. What does this interior function, and the inside function goes first. What does the interior function do to 25? Well, f of 25 is the square root of 25. And so that brings it down to a 5. Now we let the g function work on the output of what we just computed. Started with 25, that's x. Computed f of x, the square root of 25, and we got 5. And now we're going to let g work on that. But see, g of 5 is 5 squared, and that's 25. So we started with 25 and we ended with 25. And you should also establish that you can do this with a number. But I'm trying to keep this moving, so inverse functions. Here are two other inverse functions, u and v. They're linear. And to establish that these are inverse functions, since I did not provide you with a table, we'll just pick a number like 3. And we'll start with x equals 3. And we'll talk about what does u, the function u, do to the 3. Well, u is this calculation right here. It's 4 times 3 plus 2. And so u of 3 is 14. Now, if we take that 14 and plug it into the proposed inverse function v, that would be 14 minus 2 divided by 4, which is 12 divided by 4, which is 3. Now this 3 was achieved by doing what? Putting 14 into the v function. So this 3 is v of 14. But where did 14 come from? It came from putting 3 into u. So as you can see, we started with 3, we ended with 3, and that illustrates some property of inverse functions. And you'd want to be able to demonstrate that it works backwards also. I also want to illustrate how you would go about finding this inverse function if it was not given to you. This technique almost always works. You start off with y equals 4x plus 2. And in inverses, you want to trade places with x and y. So you put the x here and the y here, and then just solve this equation for y. So you'd subtract 2 from both sides. And then you would divide both sides by 4. And you would come up with the expression used for the function v, x minus 2 over 4. And it works backwards. So if we start out with v, and we trade places with x and y, so that looks like this, and then solve for y, Well, you'd multiply both sides by 4. You get 4x equals y minus 2. And you would add 2 to both sides. And you get 4x plus 2 equals y, which is exactly the expression used for the function u. Okay? One more comment. The functions I just looked at, u and v, when graphed simultaneously, have a certain sort of a symmetry with respect to this line, the y equals x, or so-called identity function. You can see that one of these lines is the reflection of the other over this y equals x line. Here are the functions f and g we looked at a minute ago. F was the square root, g was x squared. They also have that symmetry over the line y equals x. One is the reflection of the other. So we expect to see that anytime we have functions. Here's a function that doesn't have an inverse. I'm not going to do much with this function because it doesn't have an inverse. How do I know this? Okay, well, draw, for example, a horizontal line right through y equals 5. And you can see there are two x values associated with 5. There's a -1 and a +1. So if I made some table for z, among all the entries in this table, you would find these 2 points. -1 goes with 5, and somewhere down the list you'd find +1 is paired with y equals 5. And you can tell this is not a one-to-one function. So the problem becomes, if you think you have an inverse, see, in the inverse function, you should be able to turn all these pairs around backwards. In other words, 5 with -1, and then 5 with +1. Now ask yourself, if x is 5, what y does the w function assign to 5? Well, it's ambiguous. It's a 1, or maybe it's a -1, and that's because w is not a function at all. So this z function has no inverse function. But notice that if you restricted the domain, you would have an inverse function. In other words, if you just took everything to the right of the y-axis and said x's have to be greater than or equal to 0, you'd have a one-to-one function, and it would have an inverse. Okay, now we can talk about exponentials and logarithmic functions. Here's a base 2 exponential function, and here's a base 2 logarithmic function. They are inverses. Look at their tables. The 2 to the x function has these entries, among others. If you turn all these around backwards, you get some of the entries that you would find in a base 2 log function. Also, graphing 2 to the x and base 2 log of x simultaneously on the same graph, we can see that we have symmetry with respect to the y equals x line, or the identity line. They indeed are functions. Now, to demonstrate, just with one example, how these act like inverse functions, we'll pick a number out of the table like, let's pick a number that's not in the table. Let's start with x equals 5. And let's put it through this calculation here. Let's put it through this exponential function 2 to the 5th. And we get 32 for an answer. 5 factors of 2 multiplied together does make 32. Now so 2 to the x appears to make 5 grow much, much larger. We're looking for a way to restore that to what it started with. And the answer is, take the base 2 log of 32. Because when you find that log, you quite literally are asking, what exponent can you put on a 2 to make a 32? And the answer is, it's a 5. You start with a 5, you end with a 5. That's a demonstration of the inverse nature of these two functions. Now, for a minute, let's suppose I gave you 2 to the x, and I said, find the inverse. Find the inverse function. And let's pretend you didn't know it was base 2 log. How would you go about doing that? Well, you do it the same way we did a minute ago. You just trade places with x and y. So you'd start with this, and you'd say, I'm going to put an x here, and I'm going to put a y there. So 2 to the y is now equal to x, instead of 2 to the x equals y. Well, since that's an exponent on 2, that's also a logarithm. Exponents are logarithms. This is a base 2 logarithm. The base 2 logarithm of this answer over here is the exponent that you can put on 2, up above 2, to make that. And there you have your inverse. And it works the other way around also. There's quite a bit of content here, though, in today's lesson, and so I want to keep it moving. Well, we don't have to do all of these, but these are supposed to be problems where you can quickly find the inverse. So one way to go about this, which is pretty fast, is just to trade places with x and y. Write something like x equals 11 to the y power. And then just remember, you've got a base. You've got an exponent, and exponents are logs. If 11 to the y power equals x, then the base 11 log of x equals y. Bam, you've got your inverse. Here's one that says e to the 3x. Okay, do the same thing. Trade places with an x and the y. So you write e to the 3y is equal to x. Now we have a base. It's base e. We have an exponent. That's the answer to the log. And then we have the argument inside the log, which is the answer or the value of the power. So we have base e log of x equals 3y. This, of course, is natural log of x. And then divide both sides by 3, and you're done. So you get y equals natural log of x over 3. Quick, find the inverse. Well, the inverse of a base 5 log is a base 5 exponential. So the fastest way by far to do this problem is just remember that logs and exponentials are inverses. A base 5 log has as its inverse a base 5 exponential. And I could carry out all the steps and convince you that that's correct. Well, some of these down here look a little more complicated. I can go through all the steps where you trade places with x and y and write something like this. X equals base y log of x minus 1. Or, excuse me, that's y minus 1, and that's a 5. Okay, got a little carried away. Well, the base 5 log of y minus 1 equals x means that x is an exponent you can put on 5 to make whatever's inside the log. And then you just add 1 to both sides and you're done. So y equals 1 plus 5 to the x. Now this one says base 5 log of x minus 1, and the minus 1's not inside of this argument. Nevertheless, what we did before will work. Trade places with x and y. So you have x equals base 5 log of y. I would, at this point, add 1 to both sides. So now I have x plus 1 equals the base 5 log of y. And then just use the definition of logarithm. A base 5 log of something like y. If that's equal to x plus 1, then x plus 1 is the exponent that is above the 5. 5 to the x plus 1 power has to make the thing inside the log. And we're done. Okay, and then to get these last two done, just remember that these are base e logs. Natural log is a base e log. So for example, I could rewrite this problem as base e log of 2x. Then I could trade places with the y and the x. This is a good way to do it. Then I try to solve for y. Well, a base e log of 2y equaling x means that e to the x is equal to 2y. Divide by 2 and you're done. Y equals e to the x over 2. Okay? Now on this one, if I let x equals natural log of y minus 1, that's base e log of y minus 1. Well, that's a log. That's equal to a log, so that means it's an exponent above a base e. E to the x is equal to what's inside the log. Add 1 to both sides, and you're done. So y equals 1 plus e to the x. Okay, I hope I'm zoomed in enough for you on this one. Identify the correct log graph. You can check your work on the Desmos graphing website. That's a great website. And when you have an answer to this that you think is correct, you can check it by going to the graphing website, Desmos, and enter this equation. And then the way you enter it, by the way, is there's a little calculator button, and there's an option for functions. And when you hit the functions button, there's 3 columns. Go to the miscellaneous column, and you'll see base a log right there. So you can put a base 4 log into Desmos, and it'll pick out the correct graph for you. But that's pretty time consuming, and you have to have a computer in front of you or a phone. So here's another way to do it. Think of this for a minute. The base 4 log of 4 is equal to 1, because 4 to the 1 power is equal to 4. So if that's an x, that has to be the associated y on the log graph. So now you know that there's a point on a base 4 log graph that looks like 4, 1. Here's an even easier one. The base 4 log of 1 is equal to 0, because 4 to the 0 power equals 1. So when x is 1, y is 0. Almost every log graph has the point 1, 0 on it. Now this is supposed to help you pick the correct answer off this page. Looks to me like only one of these goes through the point 1, 0. And you'll notice that it also goes through the point 4, 1. So I'd pick this one. Now you can use that idea on this problem, but it's a base 1/4 log. And I'll just tell you right now, when you have a log with a base that's somewhere between 0 and 1, you're going to end up with a decreasing function. It's going to be one of these two. And why might that be? Well, just think about the base 1/4 log of 1/4. That has to be 1. Because 1/4 to the 1 power equals 1/4. So when you have this x, you would expect this y. So that means when x is behind the 1, all the way back here to 1/4, your y would have to be 1. So I think it's either this graph or this graph. But another way to do this is just stop for a minute and think about the definition of a base 1/4 log. If the base 1/4 log of x equals y, then that means this is the exponent that sits on 1/4 to make x. And I'm sure you know that 1/4 can also be written as 4 to the negative 1 power. Well, multiply these two exponents together. Negative 1 times y is negative y. Now, go back to the definition of what logarithm is and say, okay, if this is the exponent, this thing here is the log. So negative y is the base 4 log of x. X is the answer to this power. Now, multiply both sides by -1, and this is what you get. You get negative log base 4 of x. So this is related to the problem we did up above. Up here we did a base 4 log, and we picked this, and now we're saying that we have stumbled over something that should just be the opposite of the base 4 log. Well, that would flip this graph over the x-axis and make it look exactly like this. Almost done. Okay, don't forget transformations of graphs. This is we're not here to introduce this concept, just to review it quickly. If you have a graph like f of x, and I believe for this one I'm graphing f of x equals 4 over x squared plus 1. What happens if you add 3 to this as the last part of the calculation, like this? You elevate this graph. You get a vertical upward translation of 3 units. What happens if you subtract 3 from this calculation as a last detail? Well, this graph ends up being pulled down. The whole graph decreases in value. It's a vertical downward translation of 3 units. But what happens if you add 3 as, well, the first thing that you do? This graph ends up translating to the left 3 units. Whereas if you subtract 3 as a first calculation, this graph moves to the right 3 units. And when I say first calculation, for example, subtracting 3 as the first thing you do, that would look something like this. Okay? Very, very first thing I do is subtract 3. And I'm saying that this original graph centered on the y-axis would move to the right 3 units. And finally, we saw this just in the last problem, multiplying by -1 will flip the graph and reflect it over the x-axis. Actually, I think I pulled the wrong image into here. I should have put this one reflected over the x-axis. Okay, so this is actually the negative of that one, because we have a translation to the right, and then we have a reflection over the x-axis, like that. So I'll correct that right now. That's x minus 3. All right. We have to identify the correct graph for base 2 log x minus 1. What I would recommend is make sure you understand what a base 2 log looks like. So a base 2 log should have some points on it like this. The base 2 log of 1 is 0. So that's an x, that's a y. And the base 2 log of 2 is equal to 1, because 2 to the first power is 2. So you go up there and you look for a graph that's got the point 1, 0. And you look for a point that's got, a graph that's got 2, 1. Well, you're not going to find it. And that's because there's something else that's going on here. So let me quickly sketch a graph of base 2 log of x. It should go through the point 1, 0, right here. And it should go through the point 2, 1, right here. Well, we just got through talking about what's going to happen to this log if we subtract 1 from it as a very last move. This point should go down 1 unit, and this point should go down 1 unit. So now what do we have? Okay, this point is now 1, -1, and this point is now 2, 0. So here's 2, 0. Here's 1, -1. I would pick this one. Okay. So similar comments on this one. You're going to quickly figure out that a base 3 log graph has these 2 points. The base 3 log of 1 is 0. So that's an x and a y. Right? 3 to the 0 power is 1. And the base 3 log graph, or base 3 log of 3 is 1. So a base 3 log graph would look like this. It would have the point 1, 0. And it would have the point 1, 2, 3, 1. Okay, so 1, 0, and 3, 1. Now, how does this affect it? If I add 2, everything translates to the left because I'm adding 2 inside the log. So instead of 1, 0, you'll have a point back here, which is negative 1, 0. And instead of 3, 1, you'll translate this point back 2 units, and you'll have 1, 1. So I'm looking for negative 1, 0, and I'm looking for 1, 1. And that appears to be this one. All right, those are kind of hard. Desmos is your friend. Get on Desmos and try to figure those out. Gee, I see we're over 30 minutes here. Okay, this is kind of a stunt. Finding logs without a calculator that have seemingly nothing to do with base 4. In other words, if you take powers of 4, 4 to the third, for example, is 4 times 4 times 4 is 64. 4 to the fourth is 256. It appears you go right past 128. So remember, when you're solving this log, you're also trying to solve this problem. And you're going to get an answer that is not a whole number, like 2 or 3 or 4 or 5. So there's a suggestion, which is to try to go into a different base. These are both powers of 2. This is 2 to the 2. And this is what power of 2? I think it's 2 to the 7th. And so if these powers are equal and they have equal bases, then when I multiply these two together, let's call this y. 2y should equal to 7, and I divide both sides by 2, and I get y equals 3.5. And you can try that on your calculator. Let's see. What's 4 to the 3.5 power? 4 raised to the 3.5 power is 128. Okay. I'm going to do that the same way for this problem. And then I'm going to show you a shortcut on both of these. Finding the base 25 log of 125 is exactly equivalent to figuring out what exponent goes here. But 25 to the first is 25, and 25 squared is 625. So there is no whole number power of 25 that's going to equal to 125. But you know, these are both powers of 5. This is 5 squared. And 125 is 5 times 5 times 5 is 5 cubed. So let's call this exponent, which is the answer to the problem. Let's call it a y. Let's multiply these two together and set it equal to 3. Because equal powers with equal bases have to have equal exponents. 2 times y has to equal to 3. Now divide both sides by 2, and you get y equals 3 halves, or 1.5. And that's the answer to this problem. All right, what would a shortcut look like? Write this as 2 squared. So log base 2 squared of, write this as a power of 2. And then just divide these two numbers. 7 divided by 2. Here's a shortcut for this one. Instead of base 25, call it base 5 squared. Instead of 125, call this 5 to the third power. Then just divide these exponents, and you've got your answer. All right, the rest I'm going to leave up to you as exercises. We're up to 35 minutes. I apologize for going so long. My name's Eric. Hope you enjoyed this. Have a nice day.